All right, so today we're jumping into something that honestly kind of broke the AI world for a bit. It's this wild idea that completely flipped the script on how we teach machines to learn. We're talking about an AI that isn't just fed answers, it literally learns to teach itself. So yeah, let's get into it. Okay, so let's start with this. It's a huge, almost philosophical question, right? How can an AI possibly learn to recognize a cat if you never ever tell it what a cat is? Seriously, think about that. You just give it a million photos. No labels, no hints. It's one of the toughest nuts to crack in AI. And the solution? Well, it's this crazy, mind-bending loop where the AI basically becomes its own teacher. You know, for the longest time, the only way we knew how to train an AI was, well, the hard way. Supervised learning. You'd have an army of people just meticulously labeling millions and millions of images. This is a cat. This is a dog. That's a car. And yeah, it works, but man, is it expensive and slow. So the new frontier, the really exciting stuff, is called self-supervised learning. That's where the AI has to figure it all out on its own. And look, the goal here isn't just to get the AI to recognize cats or dogs. It's way deeper than that. The real prize is getting the AI to build its own rich internal understanding of the visual world. Researchers call this a good image representation. The best way to think about it is like learning the fundamentals of art. Once you get those down, you can paint, you can sculpt, you can do anything. It's the same idea here. Once the AI has that core understanding, you can use it for all sorts of things, object detection, photo editing, you name it, and you don't have to start from square one every single time. So before this big breakthrough we're talking about today, there was a king of the hill. The reigning champ in self-supervised learning was this technique called contrastive learning. This was the state of the art, you know? It was the way everyone thought you had to do it. And the whole idea was basically a game of this is like this and this is not like that. So how did that actually work? Well, it's pretty clever. You'd take a picture, let's say a dog. You'd then create two different versions of that same picture. Maybe you crop it differently or change the colors a bit. Those are your positive pairs. Then you'd grab a picture of something totally different, like a car. That's your negative pair. And the AI's entire job, its whole reason for being, was to learn one simple rule. Make the positive pairs seem similar and make the negative pairs seem as different as possible.
Yeah, the magnet analogy is perfect for this. The AI basically learns to treat two different views of the same dog like they're the north and south ends of a magnet. They just want to snap together, pull them closer. But the dog and the car, oh no, those are like two north poles. They repel. The AI learns to push them far, far apart in its own internal map of the world. And you just do that, a few million times, and eventually the AI starts to get a real gut feeling for what makes a dog a dog.
But there was a catch, a big one. For this whole magnet thing to work, you needed a ton of those negative examples for every single image. We're talking absolutely massive batch sizes, which means you need a crazy amount of computing power. It was also just super picky. If you didn't tweak the images just right, the whole thing would just fall apart. And that was the exact problem a team at DeepMind decided to tackle.
So they came in and asked this totally wild question. What if? What if you don't need the negative pairs at all? What if you just got rid of the pushing apart bit and only focused on pulling together? I mean, on the surface, that sounds like a recipe for total disaster, right? The AI would just learn that everything is the same. But their new approach, which they called BYOL, did something nobody saw coming.
They called it Bootstrap Your Own Latent, BYOL for short. And right there in their paper, they just lay it out. It gets state-of-the-art results without using negative pairs. That was the bombshell. They took the most important rule of the old method and just threw it in the trash. And they still won.
Okay, so how on earth does this not just fail completely? If you're only ever telling it things are similar, why doesn't it just learn a useless lesson that everything is one? The secret sauce is this really clever two-network system. You've got your online network, which is the student. It's actively learning. Its job is to predict what a second network, the target network, is going to say. But here's the crazy part. The target network, the teacher, is actually just a slightly older, slower version of the student network itself. It's like you're chasing your own shadow.
Okay, let's make this real. Imagine you're learning to draw, right? The online network is you, right now with a pencil in your hand making a sketch. The target network is like a slightly faded copy of the best drawing you did, say, 5 minutes ago. Your goal, right now, is to make your current sketch look like that slightly older, slightly better one. And as you get better, that target drawing also slowly gets better because it's always just a little bit behind you. You are literally chasing a target that you yourself are creating and improving. You're pulling yourself up by your own bootstraps, hence the name.
And that's the whole magic trick right there. This is the crucial point. By ditching the negative pairs, BYOL just completely removed what everyone thought was an essential piece of the puzzle. There's no more push dogs and cars apart. It's just this constant game of predicting itself. And because that target version of itself is slow-moving and stable, the whole thing doesn't just collapse into mush. It was a total game changer, a complete paradigm shift. All right, so it's a super cool idea, a really elegant theory, but does it actually work in the real world? This is where the story gets really good, because this is where BYOL went from just a clever idea to an absolute monster of a model. The proof, as they say, is in the pudding, or in this case, the data.
So, the team did what you have to do. They threw BYOL into the lion's den, the ultimate test for computer vision, the ImageNet benchmark. And they put it head-to-head with the reigning champ at the time, a big contrastive model called SimCLR.
And wow, just look at these numbers. For top 1 accuracy, which is just a fancy way of saying, did it get its number 1 guess right, BOLL smashed it. It hit 74.3%, leaving SimCLR in the dust at 69.3%. So not only did this radically simpler idea work, it worked better, way better.
But it gets even better. It wasn't just about being more accurate. See, one of the big problems with those older methods was that they were kind of fragile. They really depended on a bunch of clever little data tricks to work properly. So the researchers thought, okay, let's see what happens when we take away one of those tricks.
So they took away one of the key tricks, messing with the image colors. For SimCLR, the old champ, this was an absolute disaster. Its performance just cratered, dropping by a massive 22 points. It was basically using that color trick as a crutch, and BYOL, it barely even noticed. Its performance only dipped by about 9 points. What that tells you is that BYOL was learning something much deeper, much more real about the images, not just relying on cheap tricks.
And here's the final and maybe most important test. Remember that good representation we talked about? Well, does it actually transfer to other totally different tasks? The answer was a huge, resounding yes. Whether you're talking about object detection, semantic segmentation, or even estimating depth from a 2D image, the brain that BYOL built consistently beat the old methods. This was the real win.
So, okay, let's step back for a second. What does all this actually mean for AI? Because this wasn't just another tiny step forward. This was a giant leap. It pointed towards a totally new way of doing things, a path that was simpler, stronger, and way more efficient.
So let's just recap why BYO was such a massive deal. First, it didn't just get good results, it got new state-of-the-art results. And it did it by making things simpler, not more complicated. It works without negative pairs, the thing everyone thought was essential. It's way more robust, less picky about how you train it. And maybe biggest of all, it started to seriously close the gap with those super expensive, fully supervised models.
And we're not even done. To see how far they could push it, they trained an even bigger version of BYOL, and it hit a staggering 79.6% accuracy on ImageNet. That set a brand new benchmark for self-supervised learning, and it was getting ridiculously close to what you could achieve with full human supervision.
And that just leaves us with this one big final thought. The entire success of BYOL came from someone having the guts to question a rule that everyone else just accepted as fact. It's a perfect example of how the biggest breakthroughs sometimes come not from adding more stuff, but from taking things away, from finding a simpler, more elegant solution. So it really makes you wonder, doesn't it? What's the next fundamental rule in AI that's just waiting to be broken?